Ethereum is a distributed network of computers running software, known as nodes, that can verify blocks and transaction data. You need an application, known as a client, on your computer to run a node. Prerequisites: you should understand the concept of a peer-to-peer network and the basics of the even before diving deeper and running your own instance of an Ethereum client. Take a look at our introduction to Ethereum. What are nodes and clients? Node refers to a running piece of client software. A client is an implementation of Ethereum that verifies all transactions in each block, keeping the network secure and the data accurate. You can see a real-time view of the Ethereum network by looking at this map of nodes. Many Ethereum clients exist, in a variety of programming languages such as Go, Rust, JavaScript, Python, C#, .NET and Java. What these implementations have in common is they all follow a formal specification, originally the Ethereum Yellow Paper. This specification dictates how the Ethereum network and blockchain functions.
Learn how to build your own cryptocurrency trading bot with Python. If you've been in the cryptocurrency market for more than a few days, you probably know the feeling of the market dropping and you feel hopeless in cashing out your portfolio into a stablecoin or Bitcoin. Instead of panicking, take control of your portfolio by learning how to write powerful scripts which can instantly execute the trades you need to move in and out of positions. By the end of this tutorial, you will be equipped with tools which allow you to fully automate and control your portfolio without ever logging into your exchange accounts. This video series will walk you through the process of building each aspect of your own cryptocurrency trading bot. The Shrimpy Developer APIs are the premier crypto trading APIs in the market. Collect data across 17 plus exchanges, thousands of markets, and more. Access historical tick-by-tick trade data, old candlesticks, and order book snapshots. Execute trades in real time or use our smart order routing endpoints. Everything is at the tip of your fingers for immediate integration into your products or services. Installation: pip install Shrimpy Python quick start. All requests are synchronous. A path follows a new protocol from a particular height block number. This document describes one version of the protocol. In order to follow back the history of a path, one must reference multiple versions of this document. 3. Conventions use a number of typographical conventions for the formal notation, some of which are quite particular to the present work. The two sets of highly structured, top-level, state values are denoted with bold lowercase Greek letters. They fall into those of world state, which are denoted sigma or a variant thereupon, and those of machine state, mu. Functions operating on highly structured values are denoted with an uppercase Greek letter, for example upsilon, the Ethereum state transition function. For most functions, an uppercase letter is used, for example C, the general cost function. These may be subscripted to denote specialized variants, for example CSSTORE, the cost function for the STR operation. For specialized and possibly externally defined functions, we may format as typewriter text, for example the cake 256 hash function as per version 3 of the winning entry to the SHA-3 contest by Bertoni et al. 2011, rather than the final SHA-3 specification, is denoted cake and generally referred to as plain cake. Also, KEC 512 refers to the cake 512 hash function. Tuples are typically denoted with an uppercase letter, for example T, is used to denote an Ethereum transaction. This symbol may, if accordingly defined, be subscripted to refer to an individual component, for example Tn, denotes the nonce of said transaction. The form of the subscript is used to denote its type. For example, uppercase subscripts refer to tuples with subscriptable components. Scalars and fixed-size byte sequences, or, synonymously, arrays are denoted with a normal lowercase letter. For example, N is used in the document to denote a transaction nonce. Those with a particularly special meaning may be Greek, for example delta, the number of items required on the stack for a given operation. Arbitrary length sequences are typically denoted as a bold lowercase letter. For example, O is used to denote the byte sequence given as the output data of a message call. For particularly important values, a bold uppercase letter may be used. Throughout, we assume scalars are non-negative integers and thus belong to the set N. The set of all byte sequences is B, formally defined in Appendix B. If such a set of sequences is restricted to those of a particular length, it is denoted with a subscript. Thus the set of all byte sequences of length 32 is named B32, and the set of all non-negative integers smaller than 2256 is named N256. This is formally defined in section 4.3. Square brackets are used to index into and reference individual components or subsequences of sequences. For example, mus0 denotes the first item on the machine stack. For subsequences, ellipses are used to specify the intended range, to include elements at both limits. For example, mum0 31 denotes the first 32 items of the machine's memory. In the case of the global state sigma, which is a sequence of accounts, themselves tuples, the square brackets are used to reference an individual account. When considering variants of existing values, we follow the rule that within a given scope for definition, if we assume that the unmodified input value be denoted by the placeholder, then the modified and utilizable value is denoted as, and intermediate values would be asterisk operator, ampersand C. On very particular occasions, in order to maximize readability and only if unambiguous in meaning, we may use alphanumeric subscripts to denote intermediate values, especially those of particular note. When considering the use of existing functions, given a function f, the function f asterisk operator denotes a similar, element-wise version of the function mapping instead between sequences. It is formally defined in section 4.3. We define a number of useful functions throughout. One of the more common is L, which evaluates to the last item in the given sequence. 5. L x is identical to x parallel to -1. 4. Blocks, state and transaction shaving introduced the basic concepts behind Ethereum. We will discuss the meaning of a transaction, a block and the state in more detail. 4.1. World state. The world state is a mapping between addresses, 160-bit identifiers, and account states, a data structure serialized as RLP, see Appendix B. Though not stored on the blockchain, it is assumed that the implementation will maintain this mapping in a modified Merkle-Patricia tree, TRI, see Appendix D. The TRI requires a simple database backend that maintains a mapping of byte arrays to byte arrays. We name this underlying database the state database. This has a number of benefits. Firstly, the root node of this structure is cryptographically dependent on all internal data, and as such its hash can be used as a secure identity for the entire system state. Secondly, being an immutable data structure, it allows any previous state whose root hash is known to be recalled by simply altering the root hash accordingly. Since we store all such root hashes in the blockchain, we are able to trivially revert to old states. The account state, sigma A, comprises the following four fields: nonce, a scalar value equal to the number of transactions sent from this address, or, in the case of accounts with associated code, the number of contract creations made by this account. For account of address A in state sigma, this would be formally denoted sigma A n.balance, a scalar value equal to the number of way owned by this address. formerly denoted sigma A, B. Storage a root, a 256-bit hash of the root node of a Merkle Patricia tree that encodes the storage contents of the account, a mapping between 256-bit integer values, encoded into the trie as a mapping from the gate 256-bit hash of the 256-bit integer keys to the RLP encoded 256-bit integer values. The hash is formally denoted sigma A s.code hash, the hash of the even code of this account. This is the code that gets executed should this address receive a message call. It is immutable and thus, unlike all other fields, cannot be changed after construction. All such code fragments are.
Other projects still aim to build upon the Bitcoin network itself, leveraging the large amount of value placed in the system and the vast amount of computation that goes into the consensus mechanism. The Mastercoin project, first proposed by Willett 2013, aims to build a richer protocol involving many additional high-level features on top of the Bitcoin protocol through utilization of a number of auxiliary parts to the core protocol. The Colored Coins project, proposed by Rosenfeld et al. 2012, takes a similar but more simplified strategy, embellishing the rules of a transaction in order to break the fungibility of Bitcoin's base currency and allow the creation and tracking of tokens through a special Chroma Wallet protocol-aware piece of software. Additional work has been done in the area with discarding the Decentralization Foundation, Ripple, discussed by Boutelier and Heinz in 2014, has sought to create a federated system for currency exchange, effectively creating a new financial clearing system. It has demonstrated that high efficiency gains can be made if the decentralization premise is discarded. Early work on smart contracts has been done by Szabo 1997 and Miller 1997. Around the 1990s it became clear that algorithmic enforcement of agreements could become a significant force in human cooperation. Though no specific system was proposed to implement such a system, it was proposed that the future of law would be heavily affected by such systems. In this light, Ethereum may be seen as a general implementation of such a crypto law system. For a list of terms used in this paper, refer to Appendix A.2. The blockchain paradigm Ethereum, taken as a whole, can be viewed as a transaction-based state machine. We begin with a general as-is state and incrementally execute transactions to morph it into some current state. It is this current state which we accept as the canonical version of the world of Ethereum. The state can include such information as account balances, reputations, trust arrangements, data pertaining to information of the physical world. In short, anything that can currently be represented by a computer is admissible. Transactions thus represent a valid arc between two states. The valid part is important. There exist far more invalid state changes than valid state changes. Invalid state changes might, for example, be things such as reducing an account balance without unequal and opposite increase elsewhere. A valid state transition is one which comes about through a transaction. Formally, 1 sigma t plus 1 is identical to upsilon sigma t, where upsilon is the Ethereum state transition function. In Ethereum, upsilon, together with sigma, are considerably more powerful than any existing comparable system. Upsilon allows components to carry out arbitrary computation, while sigma allows components to store arbitrary state between transactions. Transactions are collated into blocks. Blocks are chained together using a cryptographic hash as a means of reference. Blocks function as a journal, recording a series of transactions together with the previous block and an identifier for the final state, though do not store the final state itself. That would be far too big. They also punctuate the transaction series with incentives for nodes to mine. This incentivization takes place as a state transition function, adding value to a nominated account. Mining is the process of dedicating effort, working, to bolster one series of transactions, a block, over any other potential competitor block. It is achieved thanks to a cryptographically secure proof. This scheme is known as a proof of work and is discussed in detail in section 11.5. Formally, we expand to 2 sigma t plus 1 is identical to 3 b is identical to pi sigma t b t0 t1 omega b upsilon sigma t0 t1 for pi sigma b is identical to where omega is the block finalization state transition function, a function that rewards a nominated party. B is this block, which includes a series of transactions amongst some other components, and pi is the block level state transition function. This is the basis of the blockchain paradigm, a model that forms the backbone of not only Ethereum, but all decentralized consensus-based transaction systems to date. 2.1 Value. In order to incentivize computation within the network, there needs to be an agreed method for transmitting value. To address this issue, Ethereum has an intrinsic currency, Ether, known also as ETH and sometimes referred to by the Old English overline D, the smallest subdenomination of Ether, and thus the one in which all integer values of the currency are counted, is the Wei. 1 Ether is defined as being 1018 Wei. There exist other subdenominations of Ether, multiplier name 100 Wei 1012 Zabo 1015 Fini 1018 ETH throughout the present work. Any reference to value, in the context of Ether, currency, a balance or a payment, should be assumed to be counted in WEI.2.2. Which history? Since the system is decentralized and all parties have an opportunity to create a new block on some older pre-existing block, the resultant structure is necessarily a tree of blocks. In order to form a consensus as to which path, from root, the genesis block, to leaf, the block containing the most recent transactions through this tree structure, known as the blockchain, there must be an agreed-upon scheme. If there is ever a disagreement between nodes as to which route to leaf path down the block tree is the best blockchain, then a fork occurs. This would mean that past a given point in time block, multiple states of the system may coexist, some nodes believing one block to contain the canonical transactions, other nodes believing some other block to be canonical, potentially containing radically different or incompatible transactions. This is to be avoided at all costs, as the uncertainty that would ensue would likely kill all the confidence